fine, maybe I'll say that now. I'm going to pass a note in the end of the lecture and collect your emails. I'm going to put the notes of the tutorial and some exercises which are not to be submitted or anything, but for your exercise for yourself there, and some notes from all these lectures as well. So today we're going to talk about our measure, some remindings. Okay, so let's maybe first define it. So definition. Excuse me, you need to submit a form if you are late. Okay, so a locally compact group. I assume that everyone knows what locally compact means, so I should remind you. Okay. So from now on, G is a locally compact group. Measure mu on G defined on the Borel sets there is a left R measure if the following four demands are true. First of all, most importantly, I demand that mu is invariant under the action of G from the left. Mean that for all measurable, the measure of G is the measure of E, the first thing. And now for some, let's call it regularity demands, which will assure us that we can do some stuff that we like to do with them, like integrate continuous functions. So we demand that all k inside G compact, the measure of k is finite. We demand what is known as a inner regularity for open sets. Which is saying that if U inside G is open, then the measure of U is the same as looking at the measure of K for K inside U compact, and then taking supremum. And the fourth demand is that autoregularity for general sets if inside G just a measurable set, we demand that the measure of E is the measure of quote unquote the smallest open set contained in it. Okay, so another formulation which is equivalent and actually is how you prove that such measures exist is through functionals on continuous functions that consider the space of functions from G to say R whose support is compact. And I consider a functional there from CCG to say R, who has the following properties. First of all, it's a linear functional. True that it is G left invariant. If I take a function, then integrating it is the same as integrating a left translation of it. Like LGF, evaluated at the point x is f of gx. Any questions?
So we assume that it's Borel measure?
What is the Borel measure? Yes, this measure is defined on the Borel set CG. This is the Borel measure. Thanks. And the third demands that R is in some sense continuous, meaning basically that well, you need to look at the topology in this space. So if the support of F, let me do it differently. If K inside G is compact, then there is some constant which depends only on K, such that if F is supported on K, or inside K, then IFF is less or equal than this constant times the supremum of F. Okay, so let me see some examples. Maybe I should say
When I ask for a non-example first, I mean something which satisfies one and two, but not the other regularity.
not three. Sure. Let's take G to be a group Q with the topology from R, and well, take
Which
the
is not locally compact.
It's not locally compact. If you take only rational points, then open sets contains just infinitely many points, and a set here is compact infinite only if it's finite. And so take the counting measure on this. Then 1 and 2 are true, because the cardinality of the set is not dependent on how you translate it, same for 2. But 3, if you take, for example, not 3, sorry, 4. Yes. Take the set E to be a point. So if you take any open set which contains it, it contains infinitely many points, hence the measure is infinite. But the measure of the point itself is just 1, finite. Okay? This is some examples.
I mean, I don't like that this is not locally compact, but
Well, there is a theorem which says that if you are locally compact, then you have a measure which satisfies this.
do I have a measure which is 9 but this does not satisfy? Do I have weak measures on locally compact groups? This is my concern. You have to explicitly assume this regularity, or it follows.
Well, I don't actually know, but the reason to assume it is that in the end of the day, what you do want to do with this measure is to integrate stuff with, how to say it, against it. What stuff do you want to integrate? Say continuous functions. So you want a function of this form, and there is a theorem by Rees which says that a function like this must be of the form of integrating against some measure which is of this form when you don't demand the G invariance. Okay, but I don't know the answer to your question.
Okay.
So maybe some examples. So if G is countable or most countable, the counting measure is left and right harmony. Okay. So if G is the additive group of the real, for example, then a bed measure works. And an example of similar taste, if G is, say, a circle, the Lebesgue measure also works. So I'm going to state a question, sorry. I'm questions? No? Sorry. So this is a theorem by Har. This is why these are called Har measures. If D is locally compact, such measures exist. They are unique up to a multiplicative constant. Okay. So maybe we show uniqueness now. Uniqueness follows the following way. Let mu be two such measures, and I can assume without loss of generality that one is absolutely continuous with respect to the other by taking mu and mu plus mu. Okay, should I write this? Okay, without loss of generality. So let's take f to be the Ergodic derivative, which is unique up to almost everywhere. So what I do now is that I operate on both of these measures, I push them by some element g. I have the following. I can push mu, push nu. Then g invariant, so I'll get nu. I can also write it as f times mu. The way to push this is f, so I put the inverse times the push measure by mu, and check it, which is fg inverse mu. So what this means, sorry, I think that I mix things up, so maybe I should invert the notation, which is bad, but right. So again, we see it. Mu is absolutely continuous with respect to mu. We look at the Ergodic derivative, do this calculation, and get this, because of uniqueness of Ergodic derivative, f is fg inverse almost everywhere, meaning that f is g invariant. Okay, but what g invariant functions do we have in G? Constants. So f is a constant, meaning that mu and mu are the same up to a multiplicative constant. Okay? Okay, so let us now talk about measures on homogeneity. Maybe I should raise this. So we can look at measures which satisfy the four properties there, but now defined on G1-8 instead of G. We demand G invariant from the left, etc. And we ask ourselves, do such measures exist? Then under certain circumstances, the answer is yes. But not always. If I'll have time, we'll talk about it. But what is important, for example, is that if such measure exists, it is unique. This is the same proof as what's written above there. But so such measures, let me talk about measure classes. Okay, so a measure class is, right, if mu a measure on some Borel space, let me define the sigma ideal defined by mu as all measurable sets whose mu measure is 0. mu nu are said to be equivalent if they have the same sigma here. And the measure class of mu is the set of collection of all measures which are equivalent. So maybe examples. So take your Borel space to be with the Borel sigma algebra, and take mu to be the bed measure, and take mu say to be the Gaussian measure. You find that if the integral of something like e minus c squared, do some normalization you don't care about. Then you can see that these two are equivalent basically by looking at the density here and noting that it is always finite and even bounded. It's not never zero. Okay. On Human Age, there is, in some sense, canonical measure class that you can take of it. This is the Har measure class. So you have your G, and you have your Human Age, unit space. You look at this quotient factor. Okay? And, well, if you have a measure here, you can push it here, but you don't always get something meaningful. You can get, for example, a measure which is always infinity or zero, which is it's not interesting. But you can always push a measure class and get something meaningful here. So you get the G invariant measure class and G mod H. This is something that will be important in things to come. Okay? And maybe I should also mention that there is topology on G mod H which comes just from the quotient topology from G. Okay? Okay. So let's maybe now try and come back.
So,
Yes.
how do you push measure class? I mean, you push the ideal, right?
Right, yes.
And how do you know that, I mean...
Okay, so maybe I should explain more. If you have a measure here, you can push it. You don't always get something meaningful, but you do, in some sense, get something meaningful if you look only on the null sets. Okay? So suppose you have two measures, mu and nu here, and you push them both. Okay? I claim that you get the same, if they have the same measure class, they have the same measure class here.
Yeah, but how do you see that given ideal comes from a measure?
How do you see that an ideal comes from a measure?
Maybe assume G is sigma compact.
I don't understand the question, I'm sorry.
You get an ideal,
Right.
that's clear. But how do you know that this ideal corresponds actually to some measure? Is a measure class of some measure?
Let's see.
Is there some characterization theorem that says if ideal of sets satisfies this and this and this, then it comes from a measure?
Maybe if you do assume, as I think we made, that G is sigma compact, and the measure mu is sigma finite, then we know that every sigma finite measure is actually equivalent to a probability measure. Because I can just take, I can normalize it on pieces, rings.
Sure.
Okay. And probability measures you can always push.
Okay.
And
Makes sense.
Okay. And yeah, you preserve the measure class by this normalization process. Okay. But to answer your question, how do you know from an ideal, if you are given an ideal, does it come from a measure? Well, I don't really know too much about it, but the only thing I can say this needs to be a sigma ideal. Meaning that if you have countable, well, yes. other than that, I don't know what to say. I'm sorry.
I'm happy with this.
Okay, so how does it push probability measure?
Okay, so how do you put measures in general?
So that to obtain a measure which satisfies second condition.
I'm sorry, could you repeat it?
Because we want to have a measure on
Yes.
G-mod edge or class measure which satisfies the second condition from the definition.
Right. Okay.
But it's finite on everything.
Yes.
Okay,
Yes.
sure, okay. Sure. Okay.
And maybe we should say that the topology of G-mod A is so designed that the map G to G-mod A is open.
Is open. Okay, so maybe so we have our left invariant measure on G, and but want it also to be a right invariant measure. We can't always get it. I mean, this is a property which works for, say, well, for abelian groups and for many other kinds of groups, but not in general. And in the exercise sheet that I'll put online, there's actually an example, which I maybe illustrate it now. If you look at this group, A, say, R, then, well, I should say, there is a very general formula to how to calculate Haar measures on Lie groups, if you know how to embed it in a nice way to some Euclidean space. And you can just calculate by hand to see the left and the right. But the left measure is not a right Haar measure as well. A right Haar measure has the same properties, but should be invariant on the right. Okay. So, right. If you do the calculation, the left Haar measure turns out to be dA dB over A squared, meaning that if you want to see the measure of the set, just integrate this over A. And the right Haar measure is the same but without the square. So they're not equivalent up to a constant. So how do you take care of this? Take G and G. You want to measure how much your measure is not right invariant with respect to G. So if you have your measure, you use the left Haar measure. And define it from U sub G set E to be mu of EG. Then, because the right multiplication, left multiplication commute with each other, you get a left invariant measure, which satisfies all these regularity conditions because mu satisfies them. So this is up to multiplication by scalar, the original Haar measure you started with. So let me denote the scalar by delta G. Okay. So claim. So just a second before the claim. So delta is a function which takes a point, an element from G to an element from 0 infinity, which is this scalar. Okay, so claim delta is a homomorphism. And I won't write it, but I'll say it, that if you multiply the right by GH, you can take H out, and then take G out, and you get delta G delta H up to order, which does not matter as you work in R. Okay? Should I write this maybe more explicitly or okay? So this is one. So 2, if G is compact, delta is equivalent to 1, and as a result, G is what is called unimodular, a unimodular group, meaning that the left measure is also a right Haar measure. So why is this? If you look at the image of G under delta, you should, well, sorry, I didn't show you this, but this is also a continuous homomorphism. I'm sorry. And well, why is that? Because you can measure in some sense this change by looking at integrating a function and looking at translations of this function. And if you work, say, in a CCG, space of continuous functions with compact support, then this map is continuous. So if you integrate, you get a continuous function, etc., etc. So this is a continuous homomorphism. So if you now take G to be compact, then you look at this map, then the image is compact because this is a continuous homomorphism, and it's also a subgroup because this is a homomorphism. But the only such is one. It's the trivial group. Okay? And if that is equal to A1, then this equality really, that mu is also right invariant. Okay? So another trivial statement is that if G is abelian, then the modulo character is 1, and the reason being that, well, multiplying on the left is like multiplying on the right. But maybe something which is less trivial is the following. This is a homomorphism, and we're going to an abelian group. Okay? So if I look at something of the form GH, G inverse H inverse, it must go to 1. Go to F to G, F H, F to G. H inverse, this is abelian. So, in particular, if G is the commutator of G over G, is groups, then G is unimodular. Okay? So, nice example, G being SL to R. This you'll see tomorrow in the lectures, maybe in 2 days or something. Fine? Okay, so pretty much in the next couple of days. So this is indeed the unimodular group. The left harm measure is the right harm measure. Okay, let me get one last example here, maybe. If G is countable, then G is unimodular. The reason being that the harm measure is just the countable measure. Okay, so maybe the last part of today is actually measures, not measure classes, on homogeneous spaces. So we saw the idea to show that if there is a G invariant measure which is satisfies the regularity properties on G mod A, then it's unique after scalar multiple. So let me write it as theorem, or
Can I ask that before you state a theorem of invariant measures on some homogeneous spaces, can you show us one space on which you don't have any invariant measure?
Yes, but well, I probably won't prove it, but if you take G to be SL2R and P is true, that you don't have any invariant measures within P. Okay? And this is a specific case of a more general theorem, which specifies exactly when do you have this invariant measures. But before touching it, I think I want to think something which smells like Fubini but not really is, that let L, H, and G be locally compact groups, or G is locally compact and these are closed subgroups. Okay. Suppose that there are invariant measures on G mod H mod L, and G mod L. Then for any function f for which the following equation makes sense, f on G mod L, we have that the integral of f, bless you, with respect to the Haar measure of G mod L is the same as doing the following. First, we look at G mod H. Let's denote it as G mod H, H. And then we take, integrate over H mod L. We take H mod L at no XL. And you can write here F A XL. Okay? So, hand waving. If you want to integrate the G mod L, you can first integrate, you can divide the quotient into two parts, first to H and then to L. Well, why should this be true? We already know that invariant measures are unique after multiplicative scalar. So we just need to show you that this function is not invariant, and because of Ries's theorem, there is a measure which also did this because of this. Well, if I show that this function is not invariant, then Ries's theorem will give me a measure which will be a multiplicative of mu G mod L, because it gives. So why is this left invariant? If I now take, instead of f, I take phi, which is the left translation of f by g, and maybe to save some room for phi of f, then phi of phi is exactly the integral on G mod H, integral on H mod L, phi of A XL, D measure H mod L XL, D measure on G mod H H, but this is by definition just F GA. And I take, maybe I'll call it A tilde to be GAH. Then what I have is this integral F A tilde XL B measure H mod L. And because this measure is left invariant, I get it. Exactly what I want. You get this integration formula. That's exactly phi of f. Okay? So I have 5 more minutes, and I'm sorry if I planned this wrong, but I know stuff lost. So
Why did you use the measure
inside this
bracket was a Haar measure?
That is a good question. But, don't think that I really used it here, but it couldn't make sense. But can't see it here, but this is weird. I'm sorry. You should use this here somehow, but I can't see where should you use it. I don't know. Sorry.
Probably use it. I mean, the formula need to make sense to begin with.
Okay.
To make this expression well defined, I think you ought to use it.
Yeah, but do you really?
I guess
That
it's hard for me to.
Okay. You'll have to
Just the definition of IF. I mean, you wrote a certain formula, but
but okay, but why is it well defined? Okay, yes, that yes, okay. Then if you change, you need to be able to change, say, things here by an element of age. So color in this way. This is maybe large, so I do it here.
Have 3 more blackboard.
Yes. Thank you.
Have 3 more empty blackboards.
Okay, thank you. Yes. So A L F XXL CTU.
maybe if I make it a mark, somehow there is there are two spaces, G mod H and G mod L, and there is a natural vibration from G mod H to G mod L,
Right.
and the fiber over the base point L is naturally identified with H mod L.
Right.
It's like a typical fiber, and obviously the other fibers are shifts of that one, G shifts of the same one, but somehow we identify them all and say, basically, we introduce a measure on one fiber, and we introduce shift of that measure on other fibers, but we need to make sense. We need the measure on the original fiber to be H invariant to begin with, and then we shift by G to well-defined measure on each other fiber. So this is kind of what behind the scene here.
Okay. Okay. So maybe just to finish this class, and I will state the general theorem of when do you have a measure on G mod H, and an example, a simple example. So G of locally compact group, and H inside G closed. So there's this measure, which is G invariant on G mod H, such that a formula of this kind holds, meaning that for every f in CCG, you have that the integral of f, the measure of G, is the integral of G mod H, d mu KH you have this Fubini kind stuff, if and only if the modular character of G restricted to H is the same as the modular character of H. So let me explain why this is indeed necessary, because this looks like a bit weird. Basically, the reason that this thing should hold is that, look at these two formulas, and now shift by some H from the right-hand side. Then if you do it here, you pull out this factor out, and if you do it here, you pull this factor out. And you need this to be an identity, so this needs to be the same. Okay? And it is in fact true that you have something in the other direction, that if this equation holds, then you have a measure on G naught H, and maybe the final example is that if you take G to be less than 2R, and gamma being less than 2Z, then we know that the modular character of G is 1 if we know that G is simple. And we know that the modular character of gamma is also equivalent to 1, because the measure here is just a counting measure. So we have this equality, meaning that there is a G invariant measure from G mod gamma. And this holds in general if you take G be semi-simple group, simply group say, and take gamma to be a lattice inside, or a discrete subgroup inside, countable subgroup inside. So you get this, and you have to do it, have a measure. Any questions? Sorry if I was quick, but never mind. So you're welcome to stay and ask questions now if you wish. And if you don't mind, I'll pass the note now with the email, so I can send you the full notes.
So if you have a discrete subgroup inside a locally compact group,
Yes.
then you just have to look at the.
Is the quotient map always cover?
Is the quotient map always a cover? Well, no. I mean, take H to be this is a very stupid shit.
Yeah, I mean, so that
If you assume that H is discrete, then
close.
Yeah, so I discrete subgroup.
yes. I mean, what does this mean? That this is a cover. That if you take a small neighborhood of a point here, then the pre-image is just discrete.
So this assumption should just translate to that on every component you have the same measure. Is it true? Isn't this assumption about modular
This
maps?
assumption, okay.
Is it equivalent to just saying that if I take a point in a quotient, small neighborhood, I look at the pre-image. So I take a point in the quotient, I look at the and the small neighborhood. I look at the pre-image, so I see this components of.
Okay.
So they should have the same measure. Rest of the car measure. So that I can just take.
Well, I think if you take gamma to be discrete, then what you say is true, because you actually see this structure of like patches in your group, if you want to think about it like this. But if you take, say, H to be, yeah, we're going to take even H to be like the unipotent group of something, then you get a crazy structure, or crazy for time right now at the end of the tutorial. Wait, I'm sorry. If you take G and you take H to be U that we had in class, then geometry is actually just R squared minus 0, and you don't see this. If you look at the pre-image point here, just wait a minute, sorry. Sorry, yes. If you take a pre-image of point there, then
fiber.
So the assumption is not two feedback because the modular character of A in that case is trivial is one.
And all the
I'm sorry, I should
yes.
have taken this fits out with
the powers.
You want
yeah,
You want this?
maybe take the diagonal two to inverse.
Oh,
This
Something like
starts.
Not n and inverse, I mean you want to start with 2 to the n.
yes.
So
Then yes, it will get this.
then on these pieces you don't have any boundary.
Okay, that is not closed.
It's not close, eh?
This closed?
This is
This closed?
Inside our start.
yes, it's closed. Just if you approach somewhere, something empty. Okay, any more questions? Okay, so